We're going to look at solving trigonometric equations that are a little, well, they have another step or two in them besides the ones that we've been working on. Here we've been looking so far at trig functions that look like this. The sine of x equals positive 1/2, and that's a trig equation that we know that we can solve by using the inverse, right? Therefore, the sine inverse of positive 1/2 would have to be x. That's our angle measure that makes the sine of that angle measure equals positive 1/2. And so we go back to the unit circle, we draw our circle, we look for values where the y value of the coordinate of the point on the unit circle was 1/2. That happens here at pi over 6. It also happens here at 7 pi over 6. So we've been doing those for a while. Usually we're going to find two angle measures that make this a true statement. So here x would be pi over 6 and 7 pi over 6. And that's just if we are looking at x values only, or angle measures only within one rotation. So we've been doing that. That's not difficult. We know how to solve equations like that. Here's one that is the secant of theta, which we know is 1 over the cosine of theta. So if 1 over the cosine of theta is 2, then I'm going to solve this for cosine by multiplying both sides by the cosine of theta. So those two have a value of 1. So 1 equals 2 times the cosine of theta. Now I'm going to divide both sides by 2. That has a value of 1. So the cosine of theta now equals positive 1/2. Again, I don't really take the step of writing the inverse step. It's much easier for me to ask myself for what angle measure is cosine positive 1/2. I go back to the unit circle. That's going to be this angle measure here, and for positive 1/2 I'm going to have to stay on the right side of that y-axis. That's where x values are positive. So that's pi over 3 and 5 pi over 3 are going to be my theta measures within one rotation that make that a true statement. So just a little review of the ones that we've been doing. If we don't start out with sine or cosine, we can turn whatever function that we're given into sine or cosine and then work with those problems. Here's tangent. So we want the tangent of x. So we know that the tangent inverse of 1 equals our angle measure. Here they're calling it x. So I know for tangent to be a positive 1, I know that the sine of that angle measure over the cosine of that angle measure have to be the same sign, either positive or negative, and they have to be the same value. And the only time that happens is when those values are root 2 over 2. So again, I have two possibilities for tangent to be a positive 1, and that happens in quadrant 1. Here's in quadrant 1, so I know that is a angle measure of pi over 4, and it happens in quadrant 3. Both x and y are negative in quadrant 3, so that's going to be 5 pi over 4. So two possibilities to answer that one as well. So if we have more than one trig function show up, we need to gather like terms and we need to solve for that trig function. So again, not difficult. I have 3 sine of x's on the left-hand side of my equal sign, and I have one positive sign of x on the right-hand side. So I'm going to gather like terms using good algebra. I put this sign of x over here on the left-hand side of the equal sign. I'm going to put my constant value on the right-hand side of the equal sign, meaning I need to subtract square roots of 2 from both sides. Now I'm going to combine my signs. I have 3 sine of x's minus 1 sine of x is going to leave me 2 sine of x equals negative square roots of 2. Divide both sides by 2, and that solves for the sine of x. So the sine of x equals negative square roots of 2 over 2. If I go back to my unit circle, if I want a negative y value, that's going to happen below the x-axis. So those are the two values where your y coordinate would be negative. This is 5 pi over 4. So x is 5 pi over 4, or x is 7 pi over 4. All right, let's work another example here. Find all the solutions of this trigonometric equation. This is the first time we've encountered anything where we have a squared trig equation. So anytime that we're going to solve something, let's say this was x squared plus x equals 0. If we have a quadratic function, remember we're going to get factors. I would factor this just like this. They both have an x term in them. I would factor that x term out, and then we know that we set each one of those factors equal to 0 to find the x values to make it a true statement. So here x would be 0, or x would be negative 1. So we're going to look and use this kind of idea, even though it's not x squared and x, it's tangent squared, tangent of theta squared and tangent of theta. So let me find a different color here so we can follow what I'm doing. I want to leave that work up. So if I have the tangent of theta quantity squared plus 1 tangent of theta, and that equals 0. What we've decided to do with trigonometry, so that we don't have to use parentheses all the time, we've decided instead of writing the tangent of theta like this, like we would normally just put a squared after whatever it is that we're working with, we've decided as mathematicians that we're going to move it in front of the angle measure so that we can tell the difference between whether it is the whole tangent of theta squared or whether we are putting the angle measure squared into the theta function machine. So don't get confused when you see a squared or a cubed or a 1/2 in between your trig function and your angle measure. This is what it means. It means we're taking the whole thing and raising it to that exponent value. So don't let that confuse you. All right, so let's go back here and let's solve this. Both of these terms have a tangent of theta in them, so I'm going to factor that out. If I factor out 1 tangent of theta, that leaves a tangent of theta, because tangent of theta times tangent of theta equals tangent of theta squared. If I factor a tangent of theta out of that term, that's just going to leave a 1. So there are my factors for this quadratic equation, and I'm going to set each one of those factors equal to 0, just like I did my x's. It's identical to what we did with the x's. Tangent of theta plus 1 equals 0. So the tangent inverse of 0 is 1 theta measure that I'm after. And here's tangent of theta equals negative 1, which, again, if I was going to write it as an inverse function, it would look like this. So I'm going to go back here for what angle measures is tangent equal to 0. Remember, tangent of theta is sine over cosine. So I'm looking for angle measures where the sine was 0. So let's go back to our unit circle. I know I'm running out of space, but we're going to be 0 right here at the x-axis. There's an angle measure, and there's an angle measure where our y-coordinates are 0. So theta, in this case, where the tangent of theta is 0, would be where theta equals 0 or pi. We also want to know where the tangent of theta equals -1. Well, again, it's sine over cosine. The only way we're going to get 1 is to get a root 2 over 2 over a root 2 over 2. And the only way we're going to get negative is for this one to be positive while that one's negative, or this one to be negative while that one's positive. This only happens in quadrant 2. Here's quadrant 2, or in quadrant 4. Is that right? Where they're opposite? Yeah, quadrant 2 and 4. So I'm looking for a pi over 4 iteration in quadrant 2. So I know that's 3 pi over 4. Here theta would equal 3 pi over 4. And quadrant 4, it would be 7 pi over 4. So there are four possible angle measures that would make this a true statement, that are solutions for that trig equation. Okay, let's work another example. I'll try not to fill the whole screen up so you can follow what I'm doing. So here I have 2 times the sine of theta, quantity squared, plus 3 times the sine of theta, plus 1 equals 0. I'm going to do this one just as if it were 2x squared plus 3x plus 1 equals 0. Just like the last one, I'm going to factor it. Do our rainbow thing backwards, but instead of x's, now I have sine of thetas. So I'm going to put 2 sine of theta times sine of theta. I can get it to work here. Times the sine of theta. Because when I multiply those out, 2 times the sine of theta times the sine of theta is 2 times the sine of theta squared. I know my last ones are going to be pluses, are going to be 1s, and everything has a plus in between it. So let's foil or rainbow this out. 2 times the sine of theta times the sine of theta is 2 sine of theta quantity squared. 2 sine of theta times 1 gives me 2 sine of theta. Sine of theta times 1 gives me another sine of theta. When I add those together, I have 3 sine of thetas. And then 1 times 1 is plus 1. So there are my 2 factors. I'm going to set each factor equal to 0 and then solve for theta. So 2 sine of theta plus 1 equals 0, or sine of theta plus 1 equals 0. So I have 2 sine of theta equals -1, sine of theta equals -1/2, and then I have sine of theta equals -1. So we go back to our unit circle. I am down on this end of the x-axis. So these are the 2 angle measures where my y values are going to be smaller. So I have theta equals 7 pi over 6, or theta equals 11 pi over 6. Here, sine is -1 at this quadrantal angle, so theta would be 3 pi over 2. So go back and use what you know from quadratic equations to solve these trig equations. So we're out of time. That's all there is. Now we've done some examples on working trig equations. Come to class next time and we'll work some in class together.